This is a game of life, not of people, but of shaded squares in a grid. This problem actually originates from something that a famous mathematician created called Conway's Game of Life. It's a really interesting problem from the 2022 AMC 10 and 12B. Let's take a look. Each square in a 5x5 grid is either filled or empty, and has up to 8 adjacent neighboring squares. So neighboring squares are squares that share a side or a corner. So for example, these squares are neighboring. It does not necessarily just have to be a side. And there's some rules for transformations. Number 1, any filled square with 2 or 3 filled neighbors remains filled. So for example, if we have a filled square here, this one, and it has 2 or 3 neighbors, as you can see here, this square, in this case, has 2 filled neighbors. So it will stay filled. Number 2, any empty square with exactly 3 filled neighbors becomes filled. So a filled square just needs 2 or 3 neighbors that are filled to stay alive. But an unfilled one needs 3 neighbors to become filled. So as you can see here, this square is adjacent to all 3 squares, so it will become filled when it's transformed. Similarly, but this square, for example, won't become filled. It only has 2 neighbors, 1 and 2, that are adjacent. So it will stay empty. This square has an empty square needs exactly 3 neighbors to become filled. This square has 4 neighbors, so it won't become filled. But this square does have exactly 3 neighbors. 1, 2, 3. So that one will become filled. Suppose the 5x5 grid has a border of empty squares surrounding the 3x3 subgrid. How many initial configurations will result in a transformed grid consisting of only a single filled square in the center after a single transformation? Rotations and reflections are different. What is this whole 5x5 grid and then 3x3 subgrid? Basically, all of these rows of squares are empty, and we really only care about these inside 3x3 squares, because those are the only ones that are part of our initial configuration. Right? So, okay, in that 3x3 grid over there, we're trying to transform such a configuration to just leave one filled square. Okay, remember our rules. For a filled square to stay filled, it needs 2 or 3 filled neighbors. But for an empty square to become filled, it needs 3 neighbors. So we essentially kind of have 2 big cases here. 2 big cases. Case 1, which we're going to look at first. Center square, originally empty. So this is a casework problem, and as with some other casework problems, they can be easy to mess up. Case 1, center square, originally empty. So what we're going to do here is keep big track of what we're actually trying to do. And you know how they have a 5x5 grid? Like I mentioned earlier, the only reason they have those extra set of squares on the outside is to say that basically these squares will not have any neighbors that are outside of them. So there's no neighbors that are here. There's no neighbors anywhere surrounding the 3x3 grid of squares. So we'll just draw the 3x3 square grid for now. Okay, the first case, the center square is originally empty. So for an empty square to become filled, what are the possibilities? Okay, so it has to have exactly 3 adjacent. Exactly 3, not 4, not 2, not 1, 3. So is it just that any 3 squares you fill in will work? You just fill in any set of 3 squares and will it give a valid situation where the center square does become filled? Remember, we want to have the transferred grid only a single filled square in the middle. So only this square must be filled. What does that mean? That kind of gives three conditions, which we're going to write down so it's clear. 1, 3 filled squares, of course. We already discussed this. Number 2, all current filled squares empty. Why? Because if these squares remain filled, then they won't just leave the center square being filled. There'll be some other ones too, like this one or something. And if that's filled, that's not good. So that's not allowed. Third condition. Condition number 3 is that no other filled squares are created. What does this mean? Well, for example, let's say we have this case. Let's say we have something like this. This is our initial configuration. Now, notice what happens. This square is also neighboring 3 squares. So after the transformation, this one will become filled in addition to this one. And that's not good. We don't want this one to be filled in our final configuration. We just want the center one. So this would be an example of a case that does not work. So these are essentially the 3 things we must have for this case to be true. Okay. So let's say that one square is the corner here, okay? If there's one square that's in the corner right here, what are the possibilities for the other squares? Or actually, let's take a more organized approach to this. Let's take some subcases. And the subcases will be subcase 1, 3 diagonal squares filled. That's the first subcase. 3 diagonal squares are filled. So something like this, this, this. And it actually turns out that all such configurations, you choose 4 of these corners, you choose 3 of these 4 corners, it's all symmetric because you're just leaving out one corner. They're all kind of the same thing rotated if you think about it. So basically they're not different cases. They're going to each give the same number of ways. We still count them separately, but they are not going to give different numbers of cases that work. So for such a 3 diagonal filled case like this, does it work? First of all, well, the center square. So what I'll do is in blue, I'll mark all the squares that will be filled after the transformation. So after the transformation, this square will be filled, right? Of course, the center one. It has 3 neighbors, 3 purple neighbors. Will any other, that's condition, well, condition 1 is obviously satisfied already. The second condition, all current filled become empty, besides, of course, the center one, which is not even filled. So this will, for example, this square become empty? Well, the only way a filled square stays filled is if it has 2 or 3 neighbors. And as you can see here, it has 1 neighbor and that's about it. So this condition is satisfied as well. And the third condition, no other filled squares are created. So will this square become filled? Well, for a square to become filled, it must have 3 neighbors. So for any other square to become filled, it must be adjacent to all 3 of these currently filled squares. So all 3 of the purple squares. Is this square adjacent to 3 purple squares? No. This one isn't adjacent to 3 purple ones. Neither is this one, or this one. So none of these squares are adjacent to 3 purple squares. So no other filled squares are created. All conditions are satisfied, so all of these cases work. How many of them are there? Well, there's four corners. Sorry if I said diagonals earlier. There's 4 corners, and you choose one of them not to be filled. So 4 circle. Now, let's take another case. What if only 2 of the diagonals are filled? two diagonals are filled, which means there must be one edge square, kind of, right? And let's just copy this really quickly. And again, we're going to check the same three conditions. Now, you could just do casework without this, but these conditions over here helps us stay organized and make sure we're not making any mistakes. Okay, so the next case is we have two diagonally filled ones and one edge filled ones, right? The center one can never be filled. And this is empty in the beginning. So where can the center be? Can this centerpiece, I'm just going to label it in red, can the centerpiece go here? Will this work? So now let's see if all three conditions are satisfied. Of course, the first one is satisfied. It's satisfied for all of these cases. And the second condition, all currently filled squares become empty. Is that true? Well, notice here how this square, it's adjacent to two currently filled squares, but so it's adjacent to two filled squares. So by the condition, any filled square with two or three filled neighbors remains filled. So this square has two filled neighbors. So it's going to remain filled. But that's bad, right? We only want the center square to remain filled at the end. So this case doesn't work. So we cannot have the edge there. Can we have the edge here? Well, in this case, are any currently filled squares going to remain filled? Well, this square has only one filled neighbor, this square has one filled neighbor, and this square has zero filled neighbors. So the second condition is satisfied. But what about the third one? No other filled squares created. For this not to be satisfied, we must have a square that's adjacent to three filled squares. Oh, but this square right here, it's adjacent to three filled squares. So it's going to become filled. And again, that's bad, right? We only want the center one to become filled. So this case is not satisfied. So we cannot have the edge over there, the red edge. And this case is actually symmetric. It's the same thing, just flipped. Again, this square will have three neighbors if that's the case. It's just the same case except flipped. So the only last remaining case for two diagonals filled, the only last remaining case, or why do I keep putting diagonals? I should say corners. Two corners filled. Then we must have this one be filled over here, right? Let's go back. Of course, condition one is satisfied. It's always satisfied in our over here because they were just choosing. All currently filled become empty. Well, this square has zero neighbors. This square has zero filled neighbors, and this square has zero filled neighbors. So we're good on this condition as well. And no other filled squares are created. And that only happens if there's a square that's adjacent to three filled squares, because then it becomes filled. So this square, it's not adjacent to three filled squares. This one, only two. This one, only one. This one, only one as well. This one, two. And this one is just obviously two as well. So this condition is also satisfied. So this case, all of them will work. How many cases do we have here? Well, notice how we can kind of, if you think about it, you can kind of rotate this 90 degrees to get a new configuration. You can move this blue square here, and you can kind of, in your mind, try to rotate it 90 degrees. The two purple squares on top, the blue one at the bottom. We can rotate it 90 again. The two purple squares on the right, the blue one over here. We can rotate it again. The two purple squares at the bottom over here and the blue one on top over here. Essentially, we can rotate it in 4 different ways, and they all work. So for this case, we also just have 4 ways. Now, what about if only one corner is filled? So if only one corner is filled, then we must have only one corner is filled over here. Then we must have 2 edges that are filled. Okay, so what are the cases for 2 edges? So this is a little bit more tricky now because now we're dealing with 2 edges. So the most systematic way to approach this is to say this is position 1, 2, 3, and 4. So we have to choose, let's another subcase, one corner filled. I said diagonals instead of corners for some reason a lot earlier, but it's corner, not diagonals. So 1, 2, 3, 4. There's 4 positions. We must choose 2 of them to have filled squares. So we can kind of approach this systematically. 1, 2. If both of these squares are filled, does it satisfy all 3 conditions? Well, it of course satisfies the first condition, right? And does it satisfy the second condition over here? Okay, let me just draw it in permanently. Thicker a little bit. So if this one is filled and this one is filled, of course there's going to be 3 filled squares. Are all current filled going to become empty? No, because this square has 2 filled neighbors. So this one is bad and this case does not work. 1, 2 doesn't work. So let's just erase them. 1, 2 doesn't work, but what about 1, 3? If let's say both of these are filled. Does this work? Again, the second case, well, notice how each filled squared, this filled squared is one filled neighbor. The square over here, the square on the right, the filled one here has 1 neighbor, and the one at the bottom has 0 filled neighbors. So none of them have 2 or 3 neighbors. Condition 2 is satisfied. And condition 3, no other filled squares are created. That means that there's no other empty square that has 3 filled neighbors. Oh, but this one does. This square has 3 neighbors here. So this condition is not satisfied. So 1 and 3 also doesn't work. What about 1 and 4? 1 and 4. So if 1 and if 4 are filled, then is condition 2 satisfied? Condition 2 is not satisfied immediately because this filled square has 2 neighbors. Because that filled square has 2 neighbors, then it's going to stay filled, which is not what we want. So that also doesn't work. What about 2, 4? 2, 4 means we have this one is filled and this one is filled. Notice how this is actually symmetric to one of our previous cases. And in this case, we have the square 1 condition. In this case, condition 3 fails. Condition 3 fails because this square over here has 3 neighbors that are filled. So that one will become filled, square 1. So this case doesn't work. So 2, 4 doesn't work. So 2, 4 doesn't work. What about 2, 3? 2, 3 means we have this one filled and this one filled. Does this work? Okay, let's take this case by case, or condition by condition, I mean. So firstly, are all currently filled squares going to become empty? This filled square has 0 neighbors, this filled square has 1 neighbor, and this filled square has 1 neighbor. None of them have 2 or 3, all the filled ones will become empty. Okay, we're good. No other filled squares created. None of these squares are going to be adjacent. No empty square will be adjacent to all 3 of them. And we can check all squares. None of them will be adjacent. None of these empty squares are adjacent to all 3 of the filled squares. You can try all of them. As you can see, none of them are adjacent to all 3 filled squares. So this case does work. So 2, 3, or this case does work. And the final case is 2, 4. Okay, first of all, before we move on, how many ways are there for this case? It's very similar. You can think about how this over here can be any of the 4 corners. It can be this corner, this corner, this corner, or this corner. So there's kind of 4-way rotation that you can do. Again, there's 4 ways here. Is that it for this case? Let's find out. Final case, we have to check 3 and 4. Oh, but notice how this is also symmetric to a previous case we already did. This over here, will stay filled because it has two filled neighbors. Two neighbors, so it's going to stay filled. That's not what we want. So only 4 ways for this case over here. Finally, the last case. The last case is that no corners are filled. 0. If no corners are filled, then 3 edges must be filled. And it doesn't really matter how we draw our edges that are going to be filled over here. So in this case over here, does this work? First condition, obviously satisfied. Second condition, well, immediately. Square 2 is adjacent to 2 neighbors. So that's not going to work. Okay. So then 0 corners, and all those other cases are going to be symmetric. So 0 corners will have 0 cases. Are there any other cases we're missing? We've counted the cases for 3 corners, 2 corners, and 1 corner. But the thing is like we did in 2 corners, we found the cases that have 2 of these 4 edges and 2 of these corners here. But what if the 2 corners are not adjacent like this? What if they're diagonally opposite? That's going to be another case, and this is a common mistake that people made. They forgot this diagonally opposite corner case. Okay, so for this corner case, we check all 3 conditions and see which ones. Well, of course, the first one is auto-satisfied. And let's do our same kind of analysis. So if, let's do it in red. If this square right here is filled, then what are the possibilities for the next square to be filled? Or where there's 2 corners, so there's only going to be 1 square filled. Never mind. So if this square is filled, does it work? Well, condition 1 satisfied. Are all current filled squares going to become empty? Yes, because this square 1 neighbor, this square 1 neighbor, and this square 0 neighbors. This square has no neighbors. So condition 2 satisfied. Condition 3, no other filled squares created. Basically, is there going to be a square that's adjacent? Is there going to be a square that's adjacent to all 3 of these filled squares? This one, no. This one, no. This one, no. This one, no. Basically, none of these squares are adjacent to none of the empty squares are adjacent to all 3 filled squares. So this condition is also satisfied. So this does work. So that's 0 corners is 0, but 2 corner diagonal. Well, we already have one way that works, right? That's if the central square is at 1. And now what if it's over here at 2? Well, it's kind of the same thing. It's just symmetric. If you notice how we kind of just move this square here, it's just symmetric. You're kind of just reflecting over this line here, if you think about it. You're just reflecting it, and it's the same thing. And it's not the same orientation, but it will have the same number of ways. We've got a +1 there as well. And it's actually the same thing for 3 and 4. They're all just kind of rotations of each other. If the filled square is right here at 3, then it's the same kind of thing. All 3 conditions are satisfied. There's no other filled squares created. There's all current squares, though none of them have 2 neighbors or 3 neighbors. And there's 3 filled squares. And as you guessed it, the same thing is true at 4. 1 plus 1 plus 1 plus 1. Or just 4 ways. 4 ways. But wait. This is just one possible choice of the 2 corners in a diagonal. What about if the 2 corners are here and here? That's times 2. So 4 times 2 equals 8. So there's another 8 cases. So all in all, and for this case, there's a total of 20. For the whole case, the case 1. So case 2, middle squared is filled. The middle square, or the center square, is originally filled. Okay, so if the center square is originally filled, then if the center square is originally filled, then what are the different subcases we can break it down into? Well, the different subcases are subcase 1. Okay, so the first subcase is that there's two filled squares. There's two filled squares that are filled squares that surround the center square. Two filled squares adjacent to the center filled square. Let's just write two filled squares adjacent. And then the subcase 2 is that there's three filled squares adjacent. So why? Remember how in the problem it says that for a filled square to stay for a filled square to stay filled, it has to have 2 or 3 adjacent filled squares. So we just take these cases, well, separately. First case, two filled squares adjacent. So let's say we're going to actually take this, let's say we have two diagonal squares. Let's say we have two diagonal squares, something like this. Does this work? This doesn't work. It's actually going to be the same three conditions. It's going to be similar three conditions like we have earlier here that we're going to have to check, except it's going to be just a little bit different. Let's just copy them and change them just a little bit. So these are the conditions that we must meet for the case to be successful. And I have this cool pen that lets me copy paste. Boom. And it's pasted. Oh, that's probably not very good. Let's paste it on the next page here. Boom, it's pasted. Okay. And so the cases are, it's not necessarily three filled squares, but 2 or 3 filled squares that are adjacent. All currently filled squares empty except center one, of course. And no other filled squares created, that condition still applies in its entirety. So does this satisfy case 1? 2 or 3 filled squares adjacent to the center? Yes, it does. Does it satisfy case 2? That all current filled squares become empty besides the center one? Well, this square is only adjacent to one filled square, and this one is only adjacent to one as well. Both of the other filled squares are only adjacent to one filled square, so they're both going to become empty after this. Are no other filled squares created? For that to happen, a square must be touching all 3 squares. And if you check all of them, 2, this one is only adjacent to 1, this one is adjacent to 2, this one 2, this one 1, this one 2. None of the empty squares are adjacent to more than 2 filled squares. So they're going to remain empty. No other filled squares created. Check. So this case works. And of course, because it's a diagonal, we have 2 of these. So 2 plus. And I'm just writing plus because we might have more cases, right? Now, Now, what about if the other corner was here? Will that work? Well, the key thing to notice here is that this empty square, it's adjacent to 3 filled squares. So that case will not work. Similarly, the case of having the two diagonals adjacent here also doesn't work. And the case of having 2 diagonals adjacent over here doesn't work. So the only case with both of the other 2 squares being opposite, being corners, is having them opposite to each other. Okay. Next is that there's going to be one diagonal and one not diagonal. So like one over here like this and one over here like this. Something like that. Does this work? Well, the key thing to notice here is condition 3 fails because this square over here, it's adjacent to 3 squares. That doesn't work. But will any other case of this kind work? Can we have maybe the edge here? Well, that also won't work because then now this edge is adjacent to 2 other edges. And similarly, this one won't work because this empty square will become filled, and this one won't work as well over here because then it's adjacent to 2 filled squares. So one diagonal, one not diagonal has 0. What about 2 edges? Something like this, maybe. What if the 2 edges are adjacent? Does this work? Let's see. 2 or 3 filled squares, of course. All currently filled squares become empty. Oh no, this square, it's adjacent to 2 squares now. 1, 2. And if a filled square is adjacent to 2 squares, it's going to remain filled. This one won't become empty, and case doesn't work, where the two edges are adjacent. But what if they're opposite? This surely has to work, right? Case 1 satisfied. Case 2 is also satisfied because no square is adjacent to both the other ones. This square over here is only adjacent to 1, and this one over here only 1 as well. Okay. No other filled squares created. This one. Oh, this one won't get created, but this one will. Notice how this filled square, or this empty square, sorry, is adjacent to 3 filled squares. So it's going to get filled. So that means this case doesn't work because we don't want this square to become filled. So it's just 2 here. There's no plus. Just 2 for this subcase. Now what about 3 filled squares? Okay, let's see. Let's do that better. So 3 filled squares means around the center square. So let's break it down into 2 cases here. One, none of the things are diagonals. So let's say they're all edges. None of them are diagonals. No diagonal, or sorry, I keep saying diagonal, no corner. So if they're all 3 edges and none of them are corners, does it work? No, because for example, this square, it's adjacent to not just 2 but 3 other squares. So it's gonna stay filled, which is not what we want. So the case where having no corners is definitely not allowed. Or this, yeah. So what next? The next case is to have, well, there is a corner. So 1 plus corner. And you might be wondering why I'm not dividing this further. The reason is because if we have 1 plus corner, let's just say without loss of generality, basically we can assume it can be whatever corner we want because they're all symmetric. Let's say this corner is filled. Now let's see which squares can or cannot be filled. Can this square be filled? No, because if it was filled, it'd be adjacent to 2 squares and it would stay filled. So that square can't be filled. So we put a big X there. Similarly, this square can't be filled because then it would be adjacent to 2 filled squares and it would remain filled after the transformation. What about this one? Could this one be filled? Well, no, because then the center square is adjacent to 3 filled squares and it would become filled. So this is also a no, and by symmetry, this one's also a no, right? Because if this was filled, the center square again would become filled in the transformation. Now what about this one here? Can this one be filled? Well, if this square over here was filled, then this square over here would become filled because this empty square is now adjacent to 3 other squares, so it's going to become from empty to filled. X. What about this one over here? This empty square, if this one became filled, then this square would be adjacent to 3 filled squares, and it would become filled. So that also doesn't work by symmetry. And finally, is it possible for this square right here to be filled? Does that work? There's 3 filled squares, so the condition 1 is satisfied. Are all currently filled squares going to become empty? All currently filled squares going to become empty. So the key thing, so we have to find, but the thing is here, wait, notice how this is already the case with 2 filled squares. This is not 3 filled squares. So yes, this does work like we found earlier, but there's only, notice how here we have essentially 1, 2, 3, 4, 5, 6, 7 slots remaining after we colored this corner in. And out of those 7 slots, only one of them at most can actually be filled. But we needed, in this case, we needed 3 filled squares. But in this case, 3 filled squares that are adjacent to the center one. But in this case, only 2 can work, because any one of these squares at any of these x's would immediately be bad. So therefore, this case has 0 ways. And now we just add it up. 20 plus 4, we already found that the total for this page was 20. For this case, it was 20. And the total for this case is just 2. So the overall total is just, 22. And that's our answer. Now, I know this was a lot. So let's quickly review. First case, center square originally empty. We found our 3 conditions, and then we look at all the cases where different number of corner squares are filled. And the diagonal one, of course. We don't want to forget that. Then case 2, center originally filled. We looked if there were 2 filled squares adjacent or 3 adjacent. And for 3, we had a smart little trick to simplify our casework. Overall, we added up, we get 22. Great casework problem.